Chapter 15, Low-Temperature Sterilization. Welcome to the comprehensive audio guide for Chapter 15, focusing on low-temperature sterilization. While steam sterilization remains the recognized gold standard for items that are stable under heat and moisture, the landscape of modern healthcare has evolved. Today, medical procedures rely heavily on sophisticated, high-technology instruments. These include flexible endoscopes, fiber optic light cables, complex cameras, and delicate microsurgical instruments. These complex devices typically incorporate materials such as plastics, specialized electronics, and delicate optics. These components simply cannot withstand the extreme conditions of steam sterilization, specifically the high heat ranging from 250 degrees Fahrenheit to 275 degrees Fahrenheit. 121 degrees Celsius to 135 degrees Celsius, or the intense moisture associated with steam cycles. For these heat-sensitive and moisture-sensitive items, low-temperature sterilization is strictly required. In this chapter, we will explore the technologies that utilize chemical agents, specifically gases or plasmas, rather than steam to destroy microorganisms. It is important to acknowledge that because these processes utilize toxic chemicals to achieve sterility, they present unique safety challenges compared to steam. Therefore, proper training is critical not only for effective sterilization but also to protect patients from toxic residues and to protect staff from hazardous exposure. We begin with the basic requirements for low-temperature sterilization. To be considered effective and safe for use in a healthcare setting, any low-temperature sterilization system must meet rigorous criteria. There are 8 specific requirements you must understand for your certification exam. The first requirement is efficacy. The system must be scientifically proven to kill microorganisms, including highly resistant bacterial spores, to a defined sterility assurance level, SAL. The industry standard is typically 10, 10 to the power of -6. This mathematical expression represents a probability of a 1 in a million chance of a surviving microorganism on a sterilized device. The second requirement is safety. This requirement is twofold. First, the process must be safe for the patient, meaning it leaves no toxic residues on the device that could cause harm during a procedure. Second, it must be safe for the sterile processing technician by limiting toxic emissions in the work environment. A critical part of this safety requirement is the availability and understanding of safety data sheets, SDS, for all chemicals used in the department. The third requirement is exposure monitoring. The healthcare facility must have a reliable method to monitor the concentration of the sterilant in the environment. This is essential to ensure compliance with occupational safety regulations, specifically those enforced by OSHA. The fourth requirement is sterilizer performance monitoring. The system must be capable of being monitored using the 3 standard types of indicators. You must be able to use physical, chemical, and biological indicators to verify that the necessary sterilization parameters were met for every cycle. The fifth requirement is penetration. This is a critical factor for complex instrument design. The liquid or gaseous sterilant must be able to penetrate various packaging materials and, more importantly, reach all surfaces of the device. This includes the difficult-to-access lumens of narrow, long instruments where bioburden can hide. The sixth requirement is material compatibility. The sterilization process must not damage the instruments it is intended to clean. For example, the chemical agent should not cause clouding of optical lenses, melting of plastic components, or corrosion of metal surfaces. If a material is incompatible, the device may become brittle or fail during a surgical procedure, posing a risk to the patient. The seventh requirement is adaptability. The system should be able to fit into existing facility workflows. This includes considerations for how quickly the equipment can turn over a load and whether the facility has the necessary utility infrastructure to support the unit. The eighth and final requirement is approval. The sterilization system must be cleared by the Food and Drug Administration, FDA, for use as a medical device sterilizer. With the basic requirements established, we now begin our deep dive into the first major technology, ethylene oxide, commonly abbreviated as ETO. Ethylene oxide is a colorless, flammable, and explosive gas that has served as the standard for low-temperature sterilization in healthcare since the 1950s. Despite the development of newer and faster technologies, ETO remains an essential tool in the sterile processing department because of one distinct and superior advantage: its penetration capability. Ethylene oxide has the unique ability to diffuse through long, narrow lumens and complex geometries that other low-temperature methods, such as hydrogen peroxide vapor, cannot effectively reach. For your certification exam, you must serve as a subject matter expert on how ETO functions. Specifically, you must distinguish how it kills microorganisms compared to other methods. Unlike steam, which kills by denaturing protein through heat, or hydrogen peroxide, which kills by oxidation, ethylene oxide destroys microorganisms through a specific chemical process called alkylation. Alkylation is a chemical reaction that involves the removal of hydrogen from the microorganism's chemical structure and replacing it with an alkyl group. This structural change interferes with the cell's normal metabolism and reproduction. Specifically, it renders the cell unable to metabolize nutrients or reproduce, effectively causing it to die. Because alkylation is a chemical reaction rather than a physical oxidation process, ETO is generally non-corrosive to metals, plastics, and rubber, making it highly compatible with delicate instruments. To achieve this alkylation process effectively, the sterilization cycle relies on 4 critical parameters. You must memorize these 4 variables, as the success of the cycle depends on the correct balance of each. The first critical parameter is gas concentration. The amount of ETO injected into the chamber is vital to efficacy. While specific machines vary, typical gas concentrations range from 450 to 1,200 milligrams per liter. The second critical parameter is temperature. ETO cycles operate at low heat to protect delicate instruments. The temperature is typically maintained between 98 degrees Fahrenheit and 145 degrees Fahrenheit, 37 degrees Celsius to 63 degrees Celsius. This low temperature range is exactly what preserves your heat-sensitive items from damage. The third critical parameter is relative humidity. This is arguably the most critical variable for the actual penetration of the bacterial spore. The relative humidity within the chamber must be maintained between 40% and 80%. There is a key concept here that often appears on quizzes. Microorganisms must be hydrated to be killed by ETO. If the air is too dry, the bacterial spores become desiccated, meaning dried out. When desiccated, they become highly resistant to the gas. The humidity acts as a carrier, hydrating the spore wall and allowing the ETO gas to penetrate effectively to the core of the organism. The fourth and final critical parameter is time. Because the cycle operates at such low temperatures, the chemical reaction takes significantly longer to complete. Exposure times for ETO are much longer than steam, typically ranging from 1 to 6 hours, depending on the gas concentration and the temperature used. Now that we have established the critical parameters of temperature, humidity, time, and concentration, we can examine how these variables come together during the operation of the machine. Unlike the mechanical phases of a steam cycle, the ethylene oxide cycle is a complex chemical process. It typically consists of 5 distinct stages that you should be able to identify and describe. The first stage is preconditioning, also technically known as humidification. Before any gas is introduced, the chamber is heated to the appropriate temperature, and humidity is injected. This step is vital because, as we learned, the bacterial spores must be hydrated to be susceptible to the gas. This stage prepares the load for the kill. The second stage is gas introduction. Once the load is properly conditioned, the ethylene oxide gas is injected into the chamber until the desired concentration is reached. The third stage is exposure. This is the holding period where the load is maintained at the specific parameters for the required amount of time to achieve the death of all microorganisms. The length of this stage varies based on the temperature and concentration settings. The fourth stage is exhaust. After the exposure time is complete, the gas must be actively removed from the chamber before the door can be unlocked. This is a safety phase designed to purge the free gas from the chamber. The fifth and final stage is aeration. Even after the gas is exhausted from the chamber, the devices themselves still hold residual gas within their materials. Aeration is the process of removing this residual gas. In modern equipment, which are often called all-in-one units, this aeration process happens in the same chamber immediately following the exhaust phase, ensuring the operator does not have to handle the load while it is still off-gassing. We must now transition to the most serious aspect of working with this technology, safety and OSHA regulations. Because ethylene oxide is a toxic, carcinogenic, and mutagenic gas, its use is strictly regulated. Carcinogenic means it can cause cancer, and mutagenic means it can cause reproductive defects. There are two main regulatory bodies you must distinguish. The EPA, Environmental Protection Agency, regulates emissions into the environment outside the facility. However, for your daily work and safety, OSHA, Occupational Safety and Health Administration, regulates employee exposure inside the facility. OSHA has established specific exposure limits that are guaranteed data points on your certification exam. You must memorize 3 specific numbers. The first number is the PEL, or permissible exposure limit. The maximum amount of ethylene oxide a worker may be exposed to is 1.0 part per million, ppm. This is calculated as an 8-hour time-weighted average, TWA. This means your average exposure over a standard full work shift cannot exceed 1 part per million. The second number is the STEL, or short-term excursion limit. This limit is designed to protect you from sudden, high bursts of gas. The limit is 5.0 parts per million, but this is averaged over a 15-minute period, not 8 hours. The third number is the action level, abbreviated as AL. This is the trigger point for safety protocols. The action level is set at 0.5 parts per million. If airborne concentrations in your work area reach this level, the facility is required by law to begin increased monitoring and initiate a medical surveillance program for the staff. To maintain these safety levels, specific engineering controls are required by law. Ethylene oxide sterilizers must be located in a dedicated room that has negative air pressure. Negative pressure means that air flows into the room from the corridor, keeping any potential chemical fumes contained within the room rather than drifting out into the main department. The room must also have a dedicated exhaust system that vents directly to the outside atmosphere, not into the building's general ventilation system. Finally, compliance is verified through 2 types of monitoring. The first is area monitoring, where sensors are placed in the room to detect leaks near the sterilizer or gas cylinders. The second is personnel monitoring. This involves devices worn by the employee to measure their individual exposure. For these devices to be accurate, they must be worn within the breathing zone. The breathing zone is technically defined as a sphere within a 1-foot radius of the nose. With the safety regulations and environmental controls in place, we now turn our attention to the practical handling of the devices, starting with packaging for ethylene oxide. When preparing items for ETO sterilization, the primary and absolute requirement for any packaging material is permeability. The material must be porous enough to allow the sterilant gas and moisture to freely enter the package to kill the microorganisms. Equally important, the material must allow the toxic residuals to exit the package during the aeration process. Because ethylene oxide is such a highly penetrating gas, it is compatible with a wide variety of packaging materials. Unlike hydrogen peroxide systems, which we will discuss later, ETO can penetrate cellulose. This means you are permitted to use standard paper plastic peel pouches and standard sterilization wraps that contain cellulose. You may also use Tyvek, technically known as spun-bonded polyolefin pouches, as well as various woven and non-woven fabrics. However, there are specific incompatible materials that you must strictly avoid. First, aluminum foil is strictly prohibited because it is completely impermeable to the gas. The sterilant simply cannot get through the metal. Second, glass or plastic jars must never be used. Any hermetically sealed container will prevent the gas from entering, resulting in a non-sterile item. Third, nylon is often prohibited. Nylon has poor permeability and can retain moisture, which interferes with the cycle. Once the items are packaged, we move to loading protocols. Safety begins with how you load the sterilizer cart. Because ethylene oxide is a flammable gas, the risk of ignition must be managed. You should avoid using metal carts if possible, as metal-on-metal friction can cause sparks that could ignite the gas. The recommended practice is to use metal baskets placed on plastic or chrome carts to eliminate this friction risk. Additionally, just as with steam sterilization, packs must be loaded in a way that allows for the free circulation of the gas. Packs should never touch the chamber walls. Contact with the walls can affect temperature transfer, which may overheat the device, and can potentially burn or damage the wrapper. When the cycle is finished, we encounter the highest risk of chemical exposure, unloading. If your sterilizer does not have an automatic transfer system, you must move the load immediately to the aerator. During this manual transfer, you must follow the pull, don't push rule. If you are manually transporting a cart containing a load that has just finished the sterilization cycle, you should always pull the cart rather than push it. The physics behind this rule is simple but critical. Pulling the cart creates an airflow wake or a stream of air that draws any off-gassing fumes away from your face. If you were to push the cart, you would be forcing those toxic fumes directly into your breathing zone. Once the load is safely transferred, it must undergo aeration. As we defined earlier, items sterilized in ITO are toxic immediately after the cycle and cannot be handled or used until they are aerated. Aeration is the process by which residual ethylene oxide is removed from sterilized items by subjecting them to warm air circulation in a contained cabinet. For the certification exam, you need to memorize the two standard aeration time and temperature combinations found in most sterile processing workbooks. The first option is 8 hours at 140 degrees Fahrenheit 60 degrees Celsius. The second option is 12 hours at 122 degrees Fahrenheit 50 degrees Celsius. Note the relationship: as the temperature decreases, the required time increases. A final, unbreakable rule regarding aeration is that items must never be retrieved or handled before the aeration cycle is fully complete. Interrupting the cycle puts staff at risk of chemical exposure and ensures the devices are not safe for patient use. To complete our study of ethylene oxide, we must address how to verify that the sterilization process actually worked. Just like steam sterilization, ITO requires rigorous monitoring using physical, chemical, and biological indicators. The most critical test is the biological indicator, or BI. For the certification exam, you must know the specific spore used to test ethylene oxide. That spore is Bacillus atrophius. To help you remember this, use the simple mnemonic of looking at the letter A in atrophius. Think of the A as standing for air or gas. Because of the critical safety risks and the complex nature of the chemical process, the frequency for testing is strict. A biological indicator should be run with every single load. You cannot release a load until the BI result is known. Furthermore, the placement of the test pack matters. The BI test pack should be placed in the center of the load. This is physically the most difficult area for the gas to penetrate, creating the greatest challenge to the sterilization cycle. Regarding chemical indicators, such as autoclave tape specific to ITO, you need to know the visual signal. External chemical indicators typically turn green upon exposure to the gas, distinguishing them from steam indicators which typically turn black. We now move to the second major technology in this chapter: hydrogen peroxide systems. This category includes hydrogen peroxide gas plasma systems, such as the STERID machines, and vaporized hydrogen peroxide, VH2O2, systems, such as the VPRO machines. These systems were developed as a safer and significantly faster alternative to ethylene oxide. While Ito cycles can take 12 hours or more, hydrogen peroxide cycles are rapid, typically ranging from 28 to 75 minutes. This speed allows for a much faster turnover of expensive surgical instruments. The mechanism of action is also fundamentally different. This is a critical distinction for your exam. While Ito kills by alkylation, hydrogen peroxide kills by oxidation. The process creates free radicals that interact with the cell membranes, enzymes, and nucleic acids of the microorganism, effectively destroying its life functions. You should be familiar with the standard phases of a hydrogen peroxide gas plasma cycle, as they differ from steam or Ito. There are typically 5 phases. The first phase is vacuum. All air is removed from the chamber to create a deep vacuum. The second phase is injection. A pre-measured amount of liquid hydrogen peroxide, typically at a 59% concentration, is injected into the chamber and immediately vaporized. The third phase is diffusion. The hydrogen peroxide vapor disperses throughout the chamber and contacts the devices to kill bacteria. The fourth phase is plasma. In plasma systems, radiofrequency energy is applied to the vapor. This creates plasma, which is technically defined as a fourth state of matter distinct from solid, liquid, or gas. Inside the chamber, it appears as a glowing purple cloud. The function of this plasma phase is critical. It breaks the hydrogen peroxide vapor down into non-toxic byproducts, specifically oxygen and water vapor. The fifth phase is vent. Because the plasma phase broke down the chemicals into safe byproducts, no aeration is required. It is important to note here that not all hydrogen peroxide systems use this plasma phase. Vaporized hydrogen peroxide, VH2O2, systems use the oxidative power of the vapor without generating plasma. However, the mechanism of killing, oxidation, and the material limitations remain similar to plasma systems. Once the vent phase returns the chamber to atmospheric pressure, the door can be opened, and the items are dry, safe to handle, and ready for immediate use. While the speed and safety of hydrogen peroxide systems are advantageous, they come with a significant operational limitation known as material compatibility. For the certification exam, you must fully understand the cellulose restriction. The rule is strict and absolute. You cannot process any items containing cellulose in any hydrogen peroxide system. This means materials such as paper, linens, cotton, or wood are completely prohibited. You need to understand the physics behind this rule. Cellulose absorbs the hydrogen peroxide vapor like a sponge. This absorption has a catastrophic effect on the sterilization cycle. When the packaging material absorbs the sterilant, it drastically reduces the concentration of the gas remaining in the chamber. Consequently, this causes the chamber pressure to drop. The machine's sensors will detect this drop and automatically abort, or cancel, the cycle to prevent a sterilization failure. If a cycle does abort, you must exercise extreme caution. An aborted load may contain hazardous liquid hydrogen peroxide residue on the items or packaging. You must always wear appropriate PPE, specifically chemical-resistant gloves, when handling items from a cancelled cycle to avoid chemical burns. Based on this rule, you must be vigilant about never loading specific common items. You cannot use paper plastic peel pouches. You cannot include paper instrument count sheets, which are commonly found inside surgical trays. And you certainly cannot include any cotton towels, gauze, or sponges to pad the tray. Instead of paper, you must use synthetic packaging materials that do not absorb the chemical. For pouches, Tyvek, or spun-bonded polyolefin, is the only material compatible with hydrogen peroxide. For wrapped trays, you must use specific synthetic wraps designed for low-temperature sterilization. These are typically identified by their blue color and distinct synthetic texture, which feels different from standard paper-based wraps. In addition to the material restrictions, there are critical limitations regarding lumens and moisture. Hydrogen peroxide has significantly poorer penetration capabilities than ethylene oxide. It cannot easily turn corners or travel down extremely long tubes. Therefore, the technician must strictly consult the manufacturer's instructions for use, AFU, to verify if a specific scope's lumen length and diameter are validated for that specific sterilizer model. Furthermore, items must be completely dry before entering the chamber. Because the system relies on a deep vacuum to vaporize the liquid peroxide, any moisture remaining on the instruments will boil and interfere with the process, causing the cycle to abort. Before we conclude this section, we must address the safety limits and monitoring for hydrogen peroxide. Just like ethylene oxide, OSHA has established a permissible exposure limit for this chemical. You must memorize that the limit is exactly the same as ETO, 1.0 part per million, calculated as an 8-hour time-weighted average. For sterilizer performance monitoring, you must also use a biological indicator. However, unlike ETO, which requires a BI with every load, the minimum requirement for hydrogen peroxide is typically to run a BI at least daily, though many facilities prefer to run one with every load for maximum safety. Having covered the two most common methods, we now examine the third and final low-temperature technology you need to know, ozone sterilization. Ozone, symbolized as O3, is a form of oxygen. Like hydrogen peroxide, ozone destroys microorganisms through the process of oxidation. It attacks the cell by chemically stripping electrons from the microorganism's molecules, causing the cell to break down and die. The unique operational feature of ozone sterilizers, and their primary advantage, is how the sterilant is sourced. Unlike ethylene oxide, which requires gas tanks, or hydrogen peroxide, which requires liquid cartridges, ozone sterilizers generate the sterilant internally. The machine requires only a connection to medical-grade oxygen and water. Inside the unit, these basic elements are converted into ozone gas. This means there are no chemical tanks or cartridges for the staff to inventory, handle, or dispose of, which significantly simplifies safety protocols. Regarding the cycle duration, ozone is slower than hydrogen peroxide but faster than ethylene oxide. The cycle takes approximately 4.5 hours to complete. For monitoring, the biological indicator used is Geobacillus styrothermophilus. This is the same heat-resistant spore used for steam and hydrogen peroxide, as it is highly resistant to oxidation. Finally, similar to hydrogen peroxide, no aeration is required. The machine converts the ozone back into oxygen at the end of the cycle, so items are safe to handle immediately. We have now covered the three primary low-temperature technologies, ethylene oxide, hydrogen peroxide, and ozone. To prepare you for the certification exam, we will now start a comparative review. This section is essentially a study matrix. We will compare these three methods side by side across 5 key data points that frequently appear on tests. The first data point is the killing mechanism. You must not confuse these. Ethylene oxide is the outlier here. It kills by alkylation, which is a chemical reaction that interferes with metabolism. In contrast, both hydrogen peroxide and ozone kill by oxidation, which is the process of stripping electrons. The second data point is the biological indicator spore. Again, ethylene oxide is the unique one. ETO uses Bacillus atrophius. Remember the mnemonic, A for air. In contrast, both hydrogen peroxide and ozone use Geobacillus styrothermophilus, the same spore used for steam. We continue our comparative review with the third data point, cellulose compatibility. This is a critical operational difference. For ethylene oxide, the answer is yes. Because ETO is a highly penetrating gas that does not bind with cellulose, it is compatible with paper peel pouches and paper-based sterilization wraps. This allows for standard packaging protocols. However, for both hydrogen peroxide and ozone, the answer is a strict no. Cellulose is strictly prohibited because it absorbs the sterilant and causes cycle failure. For these methods, you must use Tyvek or synthetic polypropylene wraps. The fourth data point is aeration requirements. For ethylene oxide, the answer is yes. Aeration is a critical safety step that requires significant time, either 8 hours at 140 degrees Fahrenheit or 12 hours at 122 degrees Fahrenheit. The cycle is not complete until this phase is finished. In contrast, for both hydrogen peroxide and ozone, the answer is no. These technologies break down their sterilants into non-toxic byproducts like oxygen and water vapor during the cycle itself, so items are safe to handle immediately upon door opening. The fifth and final data point is penetration capabilities. This is where ethylene oxide earns its place in the department. ITO is rated as excellent. It is currently the only method capable of sterilizing long, narrow flexible lumens without strict limitations. It is the problem solver for the most complex devices. Hydrogen peroxide is rated as good. While effective, it is generally restricted to shorter or wider lumens, and you must always verify the specific dimensions in the manufacturer's instructions. Finally, ozone is rated as limited. Its penetration power is less than the other two, so strict adherence to the instructions for use regarding lumen dimensions is mandatory. We have now completed the technical review of the sterilization methods. To finalize your mastery of Chapter 15, we will review the official definitions of key sterile processing terms found in this chapter. Understanding these precise definitions is often the difference between passing and failing a vocabulary-focused exam question. The first term is aeration. The official definition is the process by which residual ethylene oxide is removed from sterilized items by subjecting them to warm air circulation. Note that the key elements are the removal of residual gas and the use of warm air. The second term is alkylation. This is the specific killing mechanism of ethylene oxide. It is defined as a chemical reaction where hydrogen is replaced with an alkyl group, preventing the cell from metabolizing or reproducing. If you see a question asking how ITO kills, look for the word alkylation. The third term is oxidation. This serves as the counterpart to alkylation. Oxidation is defined as the process of stripping electrons from a molecule. By stripping these electrons, the chemical agent destabilizes the microorganism's cell walls and functional components, leading to cell death. You must remember that this is the specific killing mechanism for both hydrogen peroxide and ozone systems. The fourth term is permissible exposure limit, abbreviated as PEL. This is a regulatory term derived from OSHA standards. It is defined as the maximum amount or concentration of a chemical that a worker may be exposed to. For the purpose of your exam, it is helpful to remember that the PEL for both ethylene oxide and hydrogen peroxide is currently set at the same numerical value, 1.0 part per million. The fifth term is time-weighted average, abbreviated as TWA. This term explains how the permissible exposure limit is calculated. It is defined as the average concentration of a chemical in the air over an 8-hour workday. This distinction is important because it means a worker can be exposed to slightly higher levels for very short periods, provided that the average over the full shift remains low. However, this is balanced by the short-term excursion limit we discussed earlier, which caps those short bursts. The sixth and final term is polymerization. This term is unique to ethylene oxide operations. Polymerization is a chemical reaction where ITO liquid turns into a solid, sticky sludge or gel. This typically occurs if ITO cartridges are allowed to expire or if they are exposed to extreme temperatures during storage. This sludge can be disastrous for the equipment, potentially clogging the sterilizer's valves and plumbing. Therefore, understanding polymerization emphasizes the importance of strict inventory control and checking expiration dates on chemical supplies. This concludes our detailed study of the key terms. To wrap up Chapter 15, we will now perform a final concept check. I will present a summary scenario that integrates the key concepts of safety, efficacy, and material compatibility that we have discussed throughout this lecture. Imagine you are a technician processing a load containing a flexible endoscope with a long, narrow lumen and a tray of plastic cameras. You must decide which sterilization method to use. First, you consider the material. Both devices are heat sensitive, so steam is impossible. You are left with low temperature options. Second, you consider the geometry. The flexible endoscope has a lumen that exceeds the length validation for your hydrogen peroxide system. This immediately rules out hydrogen peroxide and ozone. Third, you consider the logistics. You select ethylene oxide because of its superior penetration capability for that long lumen. You must now plan for the cycle time. You know the cycle will take several hours, plus a mandatory aeration period of either 8 hours at 140 degrees Fahrenheit or 12 hours at 122 degrees Fahrenheit. Fourth, you prepare the packaging. You ensure you use a peel pouch that allows gas penetration. Since you are using Ito, you know that a standard paper plastic pouch is acceptable because Ito can penetrate cellulose. Fifth, you load the cart. You place the items in a designated metal basket on a grounded metal cart to prevent static electricity buildup. After the cycle is complete, if manual transfer is required, you strictly pull the cart to the aerator to avoid pushing toxic off-gassing fumes into your breathing zone. Finally, you set the monitor. You place a biological indicator containing Bacillus atrophius in the center of the load, the most challenging spot. You run the cycle, and upon completion, you verify the chemical indicator has turned green. This scenario encapsulates the critical thinking process required of a sterile processing technician. You have successfully navigated the complexities of low-temperature sterilization. To bring this chapter to a close, let us briefly reflect on the core responsibility you hold as a technician. Low-temperature sterilization is not just about operating complex machinery. It is about protecting patients from infection and protecting yourself from hazardous chemicals. Throughout this chapter, we have navigated the critical requirements for efficacy and safety. We have explored the deep penetration capabilities of ethylene oxide and its unique alkylation process. We have contrasted this with the rapid, oxidative power of hydrogen peroxide and ozone systems. We have also emphasized the strict operational rules, from the absolute prohibition of cellulose in peroxide cycles to the mandatory aeration times for Ito. By mastering these technologies, you ensure that even the most delicate and complex surgical instruments are safe for use. You understand not just the how, but the why behind every cycle parameter, every loading restriction, and every safety monitoring protocol. This knowledge forms the foundation of your daily practice and is essential for your certification success. This concludes our study of Chapter 15, Low Temperature Sterilization.